All right, so let's now talk about the implication of Bernoulli's principle. So Bernoulli's principle said that we can relate if we have a fluid who's flowing and we don't have any mass loss, or let's say negligible mass loss down the flow, then we can relate the pressure at any point, the velocity at any point, and the height of the flow at that point. So here we have a little simple demonstration. We have a pipe here, and I'm going to shoot some air through this pipe in order to create, the air will be the fluid that's flowing. And we're going to take a look at the pressure as a function of the diameter of the pipe. Okay. So basically we're going to combine Bernoulli's principle with the equation of continuity. Remember, the equation of continuity was basically a conservation of mass argument. It said if the fluid is flowing and we don't have any leaks out of the pipe, or we don't significant leaks out of the pipe, or we don't have any significant additions of fluid into the pipe, then the area, cross-sectional area of our pipe times the velocity has to equal a constant. So where the area of the pipe is large, like on this section or this section, compared to the area here, which is smaller. So if A times V, the area times the velocity, has to be a constant. When the area is large here, the velocity must be slow. The velocity must be high here, and the velocity must be low back over here, right? A times V has to equal a constant. So if A increases, that must mean V decreases by the same amount. Okay. All right, so Bernoulli's principle then said we could relate the pressure at any point here. So I've got three little outlets here that'll show us what the pressure is. So the pressure at any point is related to the velocity there, as well as the height. In this example, we've got no height. We're not making the fluid work against gravity in order to go up a hill or gain more speed as it goes down a hill. Okay, so it's all constant in height here. So here what we're going to learn is that where the area is small, the velocity must be high, but the pressure, Bernoulli's equation says, that must be low. Wherever we have a high V, we're going to have a lower pressure in order to have Bernoulli's equation apply at every point on the pipe. So here we have some outlets, three little outlets there. And the outlets, the amount of air flowing out of here is actually going to be small compared to the air flowing across there. So the fact that we're making the pipe leaky here is not going to matter all too much. Okay. So when I turn on the air and pump in the air, you're going to see that we're going to have a difference in pressure at the three, and the difference in pressure is going to be related to how high these balls, these little tiny plastic golf balls, will float. Okay, so let's turn on the air. Let's get our first one going. Second one, you can see it's floating higher. Okay, the pressure in here has to be high because the velocity here is low. And again, because these two cross sections are equal, we should have this one go about to the same height. So again, you're measuring from the top here to there, much higher on the two outer ones where the cross section is small, telling us that the pressure here and here is high compared to the pressure here, which is lower, because it only lifts our golf ball a little bit against gravity. Okay. So that might seem a little counterintuitive, that where the velocity is high, the pressure, why isn't the pressure high? Well, it's because those particles are moving so fast they can't exert as much pressure as they would when they were going slower. Okay? So Bernoulli's equation applies. Okay? Where we see the pressure is high, the velocity has to be lower in order to keep our Bernoulli's equation equal a constant. All right, next video.